Okay, so as I was saying, I believe we are finished up with the SI based quantities. We are supposed to start looking at derived quantities and their units. Is that the case?
Yes, sir.
Okay. So, these SI derived quantities and units are obtained by doing the following. By multiplying the base quantities, which is the mass, length, time, temperature, electric current, amount of substance, and light intensity. So you multiply those base quantities, or by dividing base quantities. That's how you obtain an SI derived quantity, by multiplying, or by dividing, or by doing both multiplication and division. You do not come up with a new quantity by carrying out an addition or a subtraction of base quantities. Addition of base quantities or subtraction of base quantities does not give you any of these derived quantities. You obtain them by multiplying or by dividing, as we are going to see through different examples. The first example we're going to look at is the area. For you to obtain a physical quantity called area, you need, in one way or another, somewhere you need to multiply length by itself, whether it's the breadth and whatever it is, but the length has to be multiplied twice. You need to multiply length by length, and since length is measured in meters, you multiply length by length, then you can see that the units for area are meters squared. Are we clear? Any formula of length, any formula of area, you search for formulas for area. Somewhere you find the length is being multiplied by itself. So twice, length times length, that gives you area. The second one is volume, a physical quantity called volume. This is derived. For you to obtain the volume, you multiply the length by itself 3 times. So length times length times length. That gives you your volume. Again, any formula of volume, there is somewhere where the length is being multiplied 3 times. Are we clear with these two, area and volume?
Yes.
So for area, you multiply the length by itself twice. Volume, length is multiplied by itself 3 times in one form or another. Of course, there are different types of lengths. For example, the length from the center of a circle to the edge of a circle, that's what you call the radius. Okay? So there are different types of lengths, but when push comes to shove, basically you're multiplying length 3 times. Okay? Then there's a quantity called density. Yes? Is there a question? Okay. Next, we move on to density. For you to obtain the density, you divide the mass of an object by its volume. So here, you are doing a division. So you have to remember 2 things. Either you multiply or you divide. So density, you divide the mass by the volume, you get the density. Velocity, you divide the length. This length, which we use for velocity, is actually something called the distance, which is the length traveled by a particular object in a particular direction, divided by how much time it has taken to cover that length. Okay? So basically, the length covered by an object divided by the time, that gives you the velocity or the speed. So here you're doing a division. You obtain something called velocity or speed. Then number 5 here, there's something called momentum in physics. So how do you work out the momentum? Well, you multiply the mass of an object times the velocity. You get the momentum. So here you're doing a multiplication. The point here is, for you to obtain a derived physical quantity, you either multiply or you divide, or you do both the multiplication and the division. You do not come up with anything new when you carry out a subtraction or you carry out an addition. Okay. Then there is acceleration here. So acceleration is actually defined a bit not like what you have seen so far here. So there is the final speed on top minus the initial speed. So what you have on top here is a subtraction. So final speed minus initial speed actually just gives you something called change in speed. That is not a new physical quantity. It's just a change in speed. Okay? Then this change in speed, we divide it by the time it has taken to carry out this change in speed. Then you get what is known as acceleration. So basically, we are dividing the change in speed by the time it has taken to carry out this change in speed. Then you get what is known as acceleration. Are we clear?
Yes, sir.
Next is force. In physics,
Yes, sir.
we define force as follows: the mass of an object multiplied by the acceleration of the object. The acceleration is the change in speed divided by how much time it has taken. So if an object has got acceleration, if an object undergoes an acceleration, which is a change in speed in a certain amount of time, that acceleration multiplied by the mass of that object gives you the force which is causing that acceleration. So here, force is equals the force which causes an acceleration is equal to the mass of that particular object multiplied by the acceleration. That's how we define force. Are we clear? We're carrying out a multiplication. Next, these two are related, pressure and stress, but they are not the same. Yes, you work them out the same way, but they're not the same. Okay, they're not the same physical quantity. But both of them, pressure or stress, you work out what the force is, then you divide by the area on which that particular force is acting. One of the differences between pressure and stress is that stress, when it comes to stress usually occurs inside an object. So the stress occurs inside an object, and the pressure is exerted on the surface of the object. So pressure is exerted outside the object, stress is inside the object. Okay? Are we clear? On one of the differences between pressure and stress. Stress occurs inside. The stress occurs inside an object. Pressure occurs outside, on the surface of the object. Okay. But either of them, we work them out the same way. The force divided by the area. So we are carrying out a division. Then here, there's work and energy. These two are related, as you are going to find out in your studies of physics during the course of the year. But in a short way, if you want to find out what the work is, you just multiply the force times the distance through which this force has been applied. Okay? Because if you apply a force on something, remember, a force will cause an object to change its velocity. So if the velocity of an object changes, there has to be some distance which has been moved. So the force you have applied times the distance which has been moved by that particular object, that gives you the work you have done. Okay? You cannot do work if there is no distance which has been moved. For the distance to be moved, a force should have been applied. Okay? So these things are related in this manner. So you are carrying out a multiplication of force times distance to get work. Then there's power. How do you get power? Well, whatever work you have done divided by how much time you have done the work. So basically, power is how fast someone is doing work. So work divided by time. Here we are carrying out a division. We are dividing work by how much time it has taken to carry out this work. So again, the principle holds. Like I have said, you come up with a derived quantity by multiplying or by dividing, not by subtracting or by addition. Are we clear? And do you have any questions so far? Can we push forward? Next is electric charge. There is something called electric charge in physics. And this electric charge is what you use to charge your phones. So how much electric charge? How do you work out the electric charge? So for you to get electric charge,
yes, there's a question.
Yes, what is it? What's the question? What's the question? Sorry? I didn't hear anything. Is the question still coming? Oh, sorry. Network. Sorry, my internet disappeared a bit. What was the question?
The question was, what's the difference between work and energy?
What's the difference between work and energy? Okay, they are not the same.
Not the difference.
Yeah, they are not the same. Now, in physics, energy and work are related, but they're not the same. When you perform work, okay, when you push something, when you're performing work, you apply a force through a particular distance. If you do this the whole day, basically you're going to use up energy. And where did the energy you're going to use up come from? It came from the food you ate for breakfast or for your lunch. So we get energy from different sources into our bodies. For example, by eating food. So when you eat food, basically what you're getting is chemical energy. And that chemical energy, when you start doing things, you start change that chemical energy into other forms. There are also other forms of energy, for example, solar energy stuff, the energy we get from the sun, or the energy we get from whatever hydroelectric energy, stuff like that. So there are different forms of energy, and we get these energies in our bodies in the form of chemical energy, for example, food. So when it comes to work is a physical way of using up energy. Okay? Work is a way of using up energy. How do you do that? You actually push things. You push things, and those things need to move through a particular distance. So work is a way of using up energy. That's what I can say. Does that answer the question?
Yes, sir.
All right. So electric charge. So for you to charge your phone, there's a question?
Yes, there's a question. What's the difference between length and distance?
What and what? Oh, length and distance. Oh, okay, I see. distance is a type, it's the length moved by an object. Okay? The length which has been moved by an object, that's what you call distance. Okay? Are we clear? Distance is actually some length which has been moved by something. When you move a particular length, when you are walking, you cover some particular length, let's say 100 meters. That's what's called distance. That's what length is. Sorry, that's what distance is. You can also have different, distance is basically a type of length. You can have a length called radius or height, or there's distance. You can have different types of lengths. Diameter, circumference, all those are types of length. It depends on what is happening. Okay. So electric charge. So electric charge, how do you obtain electric charge? Well, you obtain electric charge by multiplying the electric current times the time. So if you want to charge your phone, like I was trying to say, you need two things. You need electric current to be present, and you also need time to charge your phone. If any of these two things is not there, if there's no time, but you've got electric current, but you've got no time, you can't charge your phone. If you've got all the time in the world, but there's load shedding, which means you don't have electric current, you can't charge your phone. So for you to charge your phone, electric charge, you need electric current and you need time. So you multiply, basically it's a multiplication. Electric current times time. That's how you get electric charge. Any questions on this? So we have moved on to something called electric. Some electrical physical quantity. Then there is voltage and electromotive force. Now, voltage, hello? Voltage and electromotive force are basically related to energy, because remember, the whole point of electricity and all this stuff, everything to do with electricity, okay, is the supply of energy. That's the whole point of this electrical stuff. Voltage basically measures how much energy is given to a bunch of electrons as they pass through a point, or they pass through the battery. So how much energy are those electrons given as they pass through the battery, or how much energy do those electrons lose as they pass through a resistor or something like that. So basically, that's what voltage is. How much energy is supplied to a bunch of electrons as they pass through the battery or as they pass through a component. Okay. And how do we get the voltage? Voltage is equal to the power divided by the electric current. Hello, hey, Stanley, can you switch off your microphone? So that's voltage. Voltage is actually power divided by electric current. So here we're doing a division, okay? Then there's something called capacitance. Capacitance has to do with how much charge you can store. So capacitance is equal to the electric charge divided by the voltage. So here we are doing a division. You divide electric charge divided by voltage. Voltage is power divided by electric current. Okay. Then there's something resistance. Resistance is equal to the voltage divided by the electric current. So here again, you're carrying out a division to obtain what the resistance is. And then there's another physical quantity called conductance. Conductance is basically a measure of how good a component is a conductor of electricity. And how do we define conductance? Conductance is equal to 1 divided by the resistance. So if the resistance increases, this is supposed to be resistance. If the resistance increases, then the conductance reduces. If the resistance reduces, then the conductance increases. So conductance is 1 divided by the resistance. Okay. So that's a division. Then there's another quantity called magnetic flux. This has to do with magnets and magnetic fields. So how do we define this one? So here, magnetic flux is equal to the voltage multiplied by time. So here, there you're doing a multiplication. Then there's another quantity called magnetic flux density. Again, this is related to magnets. Magnetic flux density is equal to the magnetic flux divided by the area through which the magnetic fields or the flux is passing through. Then there's something called inductance, or if you've heard of an inductor, inductance is equal to the magnetic flux divided by the electric current. So a magnetic flux can cause a current to pass through a conductor. So here we are doing a division. So as you can see, up to this point, example 18, we have been coming up with these physical quantities which you are going to meet by doing a multiplication or doing a division. Just like the way we have said, say you obtain a derived quantity by doing a multiplication or by doing a division. Then this quantity, luminous flux or luminosity, in other words, luminous flux or luminosity, luminous flux is equal to the light intensity multiplied by the solid angle. This luminous flux is the same as the luminosity which we have here. It's the same thing here. Light intensity is equal to luminosity divided by solid angle. So you cross multiply both sides, multiply by solid angle, so you end up with light solid angle times light intensity gives you this luminosity. So that's what we're talking about. So that's a multiplication there of luminous flux. Then illuminacy is the luminosity or the luminous flux divided by the area. Then there is this catalytic activity. It's basically, I think, how much of a substance is used up in a certain amount of time, like how fast a reaction is happening. So this is the amount of substance divided by time. So how much of a substance is used up in a reaction divided by how much time the reaction takes place in. So that's a division. Then there is this one. This is an interesting one. Plane angle. Plane angle is what you call the angle, your normal angle, your day-to-day angle. So the angle is 30 degrees or 40 degrees or whatever it is. In physics, we call that the plane angle. So how do you find out what the angle is, what the plane angle is? Plane angle is equals to the circumference divided by the radius. How much circumference you have between, then divided by the radius. So if you have a part of a circle, then you divide by the radius, then it gives you the angle which that circumference makes. Are we clear? So this is a division, circumference divided by radius. That's what gives you the plane angle. The circumference is a length. This circumference, this is a type of length. The length on the surface of a circle. Okay? Then the radius is the distance from the center of the circle to the outside the surface of the circle. So these circumference and length, these are two types of length, different types of length. So we are dividing two types of length to get the plane angle. Okay. Then of course there is our solid angle. Solid angle is the area on which a source of light or whatever it is, an area divided by the radius from that area to the center of whatever surface is making up that thing. Like in this case, where we're working out solid angle. So this area is what we're interested in, this area, divided by the distance from this area to the center of the circle. So this distance, the distance squared. Remember, area, what it is? Area is length times length. Okay? That's how you obtain an area. You multiply a length by itself. So once you have an area, then you divide that area by the radius squared. So you get yourself a solid angle. Next, there's a type of temperature. So the temperature we looked at earlier, that is what we called the thermodynamic temperature. Okay. Then there is the temperature we use every day, the Celsius temperature, 20 degrees Celsius or 35 degrees Celsius. There is that one. The Celsius temperature is not the same. It's a physical quantity, yes, but it is a type of temperature. Okay. It's a physical quantity and it's a type of temperature. And how do you obtain it? Celsius temperature in degrees Celsius is equals to thermodynamic temperature in kelvins minus 273.15. What has happened? Internet. Just a minute.
Because me, I can't see this. I'm just seeing my face on the phone. No one. It's back.
Okay, so my internet card.
It's back, but where is he? Because me, I can't see him. Or is anyone who's hearing his voice?
Okay, so where did the internet cut when I was talking about what? What was I talking about when the internet cut? Where was I when it cut?
Let's be quiet, guys. Now, you want to speak. You want to start teaching us a question.
Where was I when the internet cut? Was I talking about catalytic or what is it? Where was I? Okay, so I was saying plane angle. The plane angle is your normal angle in degrees. And how do we define that in physics? Plane angle is basically based on the circumference of a circle divided by the radius of a circle. So if you get a part of your circle, then you divide by the radius of that circle. That gives you the...
I can only see the picture. Or not, but I can't get what you're saying. No, I can't get what you're saying. Your mic is off.
My microphone is off. Oh, sorry. Okay, thanks. Okay, I was asking, when the video cut, where was I? What was I talking about? When the internet cut, where was I?
Should be conduction.
Luminous flux.
Okay, luminous flux. Okay. So,
That's the sun.
alright. So that luminous flux or luminosity is, luminous flux or luminosity, same thing. Light intensity times solid angle. Okay, so here we're doing a multiplication. Then illuminacy is the luminosity or luminous flux divided by the area. I need to admit some people on which the light is falling. So here we're doing a division. Then those of you who are going to do a bit of chemistry There's something called catalytic activity. You want to measure how fast a chemical reaction is happening. Okay, so how many what's the amount of substance, how many moles have actually been used in a reaction divided by the amount of time in which those moles have been used up. That's what's called catalytic activity. So if a lot of moles have been used up in a certain amount of time, then the activity of that reaction is high. Then there's plane angle. So in physics, the plane angle is basically the angle, the one you know as theta, your normal angle, okay? So the definition of an angle is based on a circle. The definition of an angle is based on a circle. We use the circumference, how much of a circumference you have, divided by the radius. So the size of the circumference divided by the radius. This circumference might not be the whole circumference, it might be part of the circumference. Whatever part of circumference you have, then you divide by the radius, then you get yourself an angle. And this angle is measured in radians. So the circumference is a type of length. So you're dividing a length by the radius, which is also a type of length. Radius is the distance from the center of the circle to the outside, to the circumference, the surface, whatever it is. So that's distance. So you're dividing distance by distance, then you get yourself a plane angle in radians. Solid angle, on the other hand, the definition of solid angle is based on a ball. Okay? You get a football. Okay? You select an area on a football, then divide that area you have selected by the radius of the ball, the radius squared. That gives you what is known as a solid angle. Basically, this is a 3D angle on an area, on a circle. So solid angle is based on a sphere, on a ball. The definition of a solid angle is based on this area is on a ball. Okay? So on a ball, like in this case, this area is on a ball, like in this case. It doesn't matter whether it looks flat or not, because guess what? Wherever you are, the surface looks flat. But scientists tell us that the Earth is a circle. It's a ball. Okay? So the fact that something looks flat does not necessarily mean that it's not part of a circle. Okay? So you select an area, then that area divided by the radius squared of the circle on which this area is part of. A very good example is those footballs with black and white patches. So you select one of those patches, whether it's a white or a black one, divided by the radius of the ball. So the area of that patch divided by the radius of the ball, that gives you your solid angle. Are we clear on solid angle?
Yes, sir.
Yes, sir.
Okay, good. Now the other one, which I want to talk about, this one, Celsius temperature. Okay, this is a temperature. This is the type of temperature. And how do you obtain these? You obtain it from the thermodynamic temperature. So basically, this temperature is obtained from the thermodynamic temperature. And how do you do that? You do a subtraction. You subtract 273.15 from your temperature in kelvins. Whatever your temperature in kelvins is, minus 273.15, then that's going to give you a temperature in solutions. On the other hand, if you have a temperature in solutions, then you add 273.15, then it's going to give you a temperature in kelvins. So you can see what is happening here. We are doing addition or subtraction. By adding or subtracting, we're not coming up with anything new. What we have is still actually temperature. It's a type of temperature. Okay? We have not come up with something completely new. What we have is a type of temperature. Are we clear?
Yes, sir.
Yeah, we just use a different scale. Then there's something called frequency. Frequency in physics is defined as the following: 1 divided by time. Now this time is very, very important. This time is the duration between two events. If something is happening, for example, if you have got a pendulum, then you swing it one side. So the time it takes to go to one side, then come back to where it was. That time is what we are talking about. That's what's referred to as the period. Okay? So the period, which is a type of time, which is the time it takes for an object to go from one end to the other end and come back, that period, 1 divided by that period, that's what gives you frequency. Then of course there's something called absorbed dose or dose equivalent. This is defined as the energy which you get, let's say from radiation. If you go to the you go to the hospital, they want to do an X-ray of you. So how much energy is going to be shown on you, divided by your mass, or whatever the mass of the part of the body that are doing that. That's what's called the dose. So here we are doing a division. Okay, so in a nutshell, any of these physical quantities, SI derived quantities, you get them by doing a multiplication, you get them by doing a division. And of course there's another table somewhere here. This table shows you the derived quantity, which we have looked at. It shows you the symbol. You're supposed to know the symbols of these physical quantities so that you use the right symbols. Then the name of the unit name. For example, force, the units of force are pascals. Pressure, the units are pascals. Stress, pascals. The Newton is measured, the symbol is capital N. Pascal is PA. Work and energy. The work is W, energy is E, but both of them are measured in joules, and the symbol is JJ. Power, the symbol is capital P. The unit is watt, that's capital W. Then electric charge, Q. The unit is coulomb, that's capital C. Voltage, capital V. Volt, V. Then capacitance, capital C. The unit for capacitance is the farad, capital F. Resistance, R. Ohm, that's a unit name, and the symbol is omega. Conductance is capital G. The units for conductance are Siemens. Then capital A is magnetic flux, phi. The unit name is a Weber, WB. Magnetic flux density is capital B. The unit name is a Tesla, and the symbol for Tesla is capital T. Then inductance is L. Then the unit name for inductance is Henry, capital H. Flux, luminous flux, phi, measured in lumens, LM. Then illuminous is E. Then lux, LX. Then catalytic activity is measured in ketals, plane angle, theta, measured in radians. Solid angle, omega, measured in steradians. Celsius temperature, small t, measured in Celsius. Frequency, mu, measured in hertz. Absorbed dose is measured in grays, GY, and dose equivalent is measured in sieverts. Sievert. Okay. And of course, this last column here shows you the things, what they're equivalent to. Meter squared, meter cubic, kg meter cubic, meters per second, meters per second squared, like that. These equivalents. That. So you need to know some of these equivalents, if not all of them. Okay. Are we clear on the SI based quantities, derived quantities? Do you have any questions?
Yes, sir, we are clear.
Okay. The other thing to note is some of these units are named after people. Okay? For example, Newton. Newton is the name of a person. So if a unit is named after a person, then the symbol for that unit is capitalized. Like the Newton is capital N. Pascal is the name of a person, so that's why it starts with capital P, then A. Joule is the name of a person, that's why it starts with capital J. Watt is the name of a person, that's why it's capital W. Coulomb is the name of a person, that's why it's capital C. Volt is named after Volta, an Italian guy, that's why it's capital V. Farad is named after Michael Farad, an English scientist, that's why it's capital F. Of course, the home is something else. Siemens, capital S. Siemens, probably some German guy or something. Then Weber is the name of a person, that's why it's WT. Tesla, I'm not sure, but it's capital T. Henry, definitely the name of a person, capital H. Then, of course, there is Hayes here. Not just Hayes, there's Celsius. Celsius is the name of a person. Andreas Celsius, some Swedish scientist who came up with the Celsius temperature scale. Okay, that's why the symbol is capital C. We say degrees capital C. You don't say degrees and small c's. Degrees capital C, because that C, which stands for Celsius, that is the name of a person. Then there is Gabriel, I think Friedrich Hess. This was a German guy, okay, a German scientist. So that's why it starts with capital H, then Z. Then Gray, I think it's the name of a person, GY. Then this one also, Civet, that's also the name of a person, starts with S and V. Are we clear?
Yes, sir.
Units named after people, they start with a capital letter when you write their symbols. It's either one capital letter, or if the unit has got more than one name, one letter, the first letter is capitalized. Okay. The other thing we want to look at is something called standard power prefixes. Now, standard power prefixes are what we use in order to express very, very large physical quantities or very, very small physical quantities. Okay. For example, kilometer, these prefixes. A prefix is something you put in front of something. Okay. A prefix is something you put in front of something. So in our case, we put these prefixes in front of the unit. For example, the unit for length, the SI unit for length is the meter. But if I'm talking about very, very large lengths, I could say kilometer. That kilo I've put in front of the meter means 1,000 meters. Are we clear?
Yes, sir.
There is also other things you could use if you want to express a very, very small length, like a centimeter. A centimeter is 1 meter, then you chop you chop the 1 meter into 100 equal parts. Then each of those equal parts, that's what a centimeter is. So if you want to express some small length, you might say 30 centimeter. 30 centi means a meter which has been chopped into 100 equal parts. Then you're using that small part as a unit of your length, whatever it is. So let's see what it is which we use. So we'll start with the prefixes we use for expressing very large physical quantities. For example, there's a factor 10. The name of this factor is deca, the symbol is dA. Then there's hector, that is 10 to the power 2, which is 100. Then the name is hector, the symbol is H. Then 10 to the power 3, this is a kilo, 1,000. Then the symbol is K. Then 10 to the power 6, that's a mega, a million, the symbol is capital M. Then 10 to the power 9, that's a giga, capital G. Then 10 to the power 12, that's a tera, capital T. Then 10 to the power 15, a penta, capital P. Then 10 to the power 18, exa, capital E. 10 to the power 21, zeta, capital Z. 10 to the power 24, iota, capital Y. Are we clear with this one? So if you want to say a million meter, in physics you'd say megameters. Okay, not million meters. or a billion meters, you'd say gigameters. Are we clear? For example, right now we are, with this load shedding thing, we are always talking about power, how much power we need. That power is measured in megawatts or gigawatts or kilowatts. This kilowatts, the watts, the unit for power. Where is power? Power is here, the watt. So you put that in front, so it becomes kilowatt. If you hear people mentioning about how much power the country needs, they're talking in terms of kilowatts, or this power station, this solar power station is going to generate 50 kilowatts of power, or it's going to generate 200 megawatts of power, stuff like that, or gigawatts of power. Are we clear?
Yes, sir.
Okay.
Yes.
There are also other factors we use to express very, very small physical quantities. Okay. This one, the deca, that is, you get a meter, then 10 times, that's a deca. But when it comes to this, 10 to the power minus 1, basically you get a meter, then you chop your meter into 10 equal parts. Okay, you get your meter, whatever your meter row is, then you cut your meter row into 10 equal parts. Each of those things you have, those parts, is what's called a deci. D. If you get your meter, then you chop your meter into 100 equal parts, because this 10 to the power minus 2, this is 1 over 100. This 10 to the power minus 1 is 1 over 10. So this 10 to the power minus 2, this is 1 over 100. You get your meter, then you chop your meter into 100 equal parts. Okay? Each of those parts, after you chop your meter into 100 equal parts, that's what's called a centi. Then this one, 10 to the power minus 3, you get your meter, then you chop it into 1,000 equal parts. 10 to the power minus 3 is the same as 1 over 1,000. So you get your meter row, you chop it into 1,000 equal parts, then each of those parts, that's what's called a milli. 10 to the power minus 6, you get your meter, you chop into 1,000,000 equal parts, then each of those is what you call a micro. So you have 1 meter row, you chop it into 1,000,000 equal bits, then each of those bits, that's what's called a micro. So same thing goes for 10 to the power minus 9, you chop your meter row into 1,000,000,000 equal parts, then each of those parts is what's called a nano. The symbol is N. This is pronounced mu, Greek. Then 10 to the power minus 12, this is what's called a pico. Same, a trillion. Get your thing, chop it into 1,000,000,000 equal parts, then each of those things, that's what's called that. Then 10 to the power minus 15, femto, symbol F. 10 to the power minus 18, atto, symbol A. 10 to the power minus 21, zepto, symbol small z. 10 to the power minus 24, yocto, small 1. So this allows you to express sizes, okay? Whether it's the size of a cell in a body or red blood cells, I don't know, small things. What's their radius, what's their diameter? So you are going to express them using these factors: micro, milli, nano, pico, like that, centimeter, like that. Are we clear?
Yes, sir.
Do we have any questions? We have come to the end.
Yes, sir.
What's the question?
I have a question, sir.
Yes.
I can see the notes you taught on the first lecture.
What?
I can see the notes you taught on the first lecture on the Moodle. How do I find them?
They're on Moodle.
Yeah, the notes you taught on the first lecture, physics first lecture.
Yes, they're on Moodle. They are there. Go under PHY 1010.
There is no video for YouTube.
I think something must have happened to the first video. I think it got damaged or something like that.
Okay, thank you.
So there's a video there. Then this is going to be the second video I'm going to put there. But there was another class before that. So one of the classes, the video got damaged, I think.
So there is nothing you can do to press it.
There is a video there.
Okay.
Yeah. So there is something which says YouTube. Then something. So you click on that. And in Moodle. Then it's going to take you to where the YouTube video is. Any other question? Do we have any other questions? Okay, so if you don't have any other questions, we come to the end. Then our next class is going to be, I think tomorrow. Yeah, our next class is going to be tomorrow. So tomorrow we'll start a new topic, scalars and vectors. It's already there on Moodle, so please download it, download the lecture notes, print them out and have a look at them. Check out the things you don't understand so that you can ask questions. Okay.
Okay, sir.
All right, so see you tomorrow at 17.